And we're back talking about section 3.1, introducing the derivative. Our last video reached the maximum amount of time, so here I am picking up the second half of that same discussion of section 3.1. And what I was mentioning as we got cut off was that we had two x values, x and x plus h, where the distance between those two values is the h, and we want that distance to go to 0. So we want these 2 points to get closer and closer and closer to each other as we're calculating the slope of the tangent line. So we begin by imagining calculating the secant, or the slope of the secant, between those two original points. And as the h value goes to 0, the distance between those points becomes 0 until eventually we are at the value x itself and we have the slope of its tangent line. So to actually calculate the derivative f prime of x, or the slope of the tangent line at x, what we're doing is we're taking the slope of the secant line between x and x plus h, and we're finding the limit as the distance between those two values, h, goes to 0. So let me remind you how we calculate the slope of a secant line. We subtract the y values of the 2 points, and then we subtract the x values of the 2 points, giving us the slope of the secant. So here's my y value for the second point, my y value for the first, I'm subtracting those, and then here are my x values, and I'm subtracting those as well. So this is all giving me the slope of the secant, but then to get the slope of the tangent, I need that h value to go to 0, and I need to find the limit as that happens. Now you'll notice here that I did a quick simplification, because if I have x plus h and I take x away from that, I'm really just left with h. So this right here is the formal definition of the derivative. A formal definition of a derivative. So to find a derivative, we're taking the limit as h approaches 0 of the slope of the secant line between x and x plus h. Alright, next up we're going to take a look at a very specific example where we do calculate the derivative using this formal definition. Okay, so we're going to start off with a function, and that function that I chose was x squared. F of x equals x squared. So we're all familiar with this parabola, this quadratic function, very basic. We know what the graph looks like. And again, what we want to do is we want to write the equation of the derivative. So we have the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, that's the formula that we're using in order to write this derivative. So what I need to start by doing is calculating my f of x plus h and my f of x. Okay, so these are both y values that go along with our x values, and we don't know what those are. So we have to figure out what that is. If you can remember doing that when you calculated the average rate of change, you had to do that same thing. You were given two numbers for x values, and you had to plug them back into the original function in order to get their corresponding y's so that you could put them in the formula and subtract them to get the slope. So let's do the same thing here. I want to figure out what f of x plus h is. So that means that I'm taking x plus h and I'm subbing it into my original function f, which is x squared. So what that looks like is x plus h squared. Now we do actually want to multiply that all out, and so you'll have to remember quickly how to square out binomials such as these, and I'm sure once you do a few of them it'll all come back. But we're FOILing, if you're familiar with that process, x squared plus 2xh plus h squared when I do it quickly. So that is f of x plus h, and that's going to get plugged in right here. All right, now we also need f of x. This one is much easier to calculate because f of x is just the function itself, x squared. We're not plugging anything into that. So that's going to get plugged in right here. All right, so continuing on, what we have is the limit as h approaches 0 of f of x plus h, which remember is x squared plus 2xh plus h squared. And I'm subtracting my second y value, which is f of x, and I'm dividing all of that by h. So all that we have left to do is just a little bit of algebra. We need to do this polynomial subtraction, and we need to divide that all by h. So let's do that. If I subtract x squared plus 2xh plus h squared by x squared, then basically those are just canceling out. And what you should always notice is that once you've done that, everything left over in the numerator should be divisible by h. And that's our next step. So let's divide each of those terms by h. Which gives me 2x plus h. The denominator canceled out because, again, I divided each term by that h. All right, now we are ready to take the limit. Once we've simplified all that's inside, we actually want to do the limit. Now this is linear, and we learned how to calculate those limits algebraically. We want h to approach 0. We can just do a direct substitution. 0 in for h. And all that we're left with is 2x. So, if f of x is x squared, which was our original function, then the derivative of that function, f prime of x, is 2x. And for those of you who've taken calculus before, I'm sure you remember the shortcut for finding the derivative of this function, and you can see that that does give you 2x. But again, the focus of this particular section is to understand what the derivative is and where it comes from in terms of limits. So next week we will surely do those shortcuts, but for now we're going to do a few examples along with. So let me tell you what this just found here, what this is, this 2x. So that represents the slope of the tangent line, or the instantaneous rate of change, at any x value where this function is differentiable. So for right now, we didn't look at a specific x value. We just said any x value we choose, we can calculate the slope of the tangent line for x squared by taking 2 times x. So what happens next is that we're going to take a look at a specific x value, and we're going to find the actual slope numerically, not just the equation for how to find the slope, but the actual slope value, as well as writing the equation of the tangent line. Okay, so same example, really, in terms of equation. So the example continued. So we've got f of x equaling x squared, and we found that f prime of x equals 2x. So we just calculated that. So in problems like these, don't expect for this to be given to you. It is something that would be step number 1, calculate the derivative. And then here's what we're going to do with it. So the directions are to find the slope of the tangent line, at x equals 1. So we have a specific value, x equals 1. Then let's also find the equation of the tangent line at that same value. All right, so we found out that for any point along the curve of x squared, we can get its slope, its instantaneous rate of change, the slope of its tangent, by doing 2x. Let's calculate that specifically for x equals 1. So, again, the slope of the tangent line at x equals 1 can be found by doing f prime of x, or in other words, 2 times x, which gives us 2. So the slope of the tangent line at that specific point is going to be 2. If we change the x value, we're going to get a different slope. Because think about the graph of x squared. Y equals x squared. I have it here on my calculator. Obviously, we can picture it in our heads. The slope changes. All right, these are not straight lines, so we don't have constant slopes. The slope changes as we move along the curve. So at x equals 1, the slope is 2. At x equals 2, the slope is now 4. It's a steeper tangent line here than it is here. Okay, so we know the slope of the tangent line. Let's write the equation of the tangent line at that point. So think about your point slope formula. Y minus y1 equals m times x minus x1. That's how we calculate the slope, or I'm sorry, that's how we write the equation of a line, is using the point slope formula. So the point that we're interested in is the point where x equals 1. The slope we found just a second ago was 2. So in order to use the point slope formula to write the equation of the line, I need to figure out what my corresponding y value is. So let's do that by finding f of 1, or in other words, 1 squared, which is 1. All right, so y minus y1 equals m times x minus x1. Plug in your point, plug in your slope, and simplify to write the equation of this line. So I'm going to distribute here, and I'm going to get y by itself. And there we have the equation of the tangent line for the curve x squared at x equals 1. And let me just graph that here. I'm going to do it on the calculator so it's precise. And there it is. So we see here is x equals 1, and here is the tangent line, the equation of it, and the slope is 2. Okay, let's do one more example here before we wrap up. This so happened to be a fairly easy one to calculate using this method, x squared. Let's make it a little bit more complicated. Okay, so let's let f of x equal x cubed plus 4x. And then let's find 3 things. Let's find f prime of x. So first of all, the overall derivative at any point x on that graph. And then let's find f prime of 1. So let's find the slope of the tangent line specifically at the value 1. And then let's find the equation of the tangent line at that same point, x equals 1. All right, so going back to our definition of the derivative, we have the limit as h approaches 0 of f of x plus h minus f of x over h And in order to start using this